Hi, everybody, and welcome to our next lecture in CHY 113. To start off today's lecture, I wanted to just bring in a world-renowned expert on all things general chemistry. This little guy here is Henry. Yeah, Henry is a true pandemic baby. He was born in mid-March. Just as we went into the hospital, things were kind of just picking up a little bit. But by the time we left with him, the entire hospital was shut down and we weren't even allowed to leave our rooms. And so he has added quite a dimension to the pandemic in general and certainly our lives. But he just wanted to say hi and to say that if ever there's a time that that his daddy doesn't respond to you as soon as you would hope, it's probably because he is cleaning out this little guy's poop. Yeah. All right. And so, as always, we're going to start today with looking at some warm-up questions. So as you try to name these compounds, I am just going to go ahead and put you on pause and hand him back to his mother. So as always, just pause the video now and try to write the formula for these following compounds. Say bye, Henry. Bye, Henry. Okay, I hope you enjoyed that little visit, and I also hope that you were able to write the formula for these compounds, and here are the answers. And so hopefully you were able to come up with those. If you weren't, as always, go back and check out some of the rules and see where you might have went wrong. Next, we're going to go in the opposite direction. I want you to write the chemical formula for these compounds. So pause the video and see what you can come up with for these chemical formulas. And hopefully you came up with these formulas. Just to hit some of these quickly, since I think it's a little more difficult sometimes coming up with the names. And oops, sorry, I realized that the titles of those are wrong. So hopefully you came up with the fact that you're supposed to write the names for these instead of the chemical formulas. But it is a little bit more difficult sometimes to come up with the names, just because of the rules start to get a little bit more particular. And so I picked these three in the beginning so that you could differentiate between just sort of a straight metal to non-metal ionic compound. Here we have a transition metal, so we have to indicate the charge of the metal, iron 2. And we figure that out by knowing that the charge on the chloride is -1. Here we have a molecular compound made up of 2 nonmetals, so now we have to use our mono, di, tri prefixes, etc. And these two I included just to show what a difference there is in names that are very, very similar, but iron 3 nitrate versus iron 3 nitride. So very, very similar names, but very, very different compounds. And then finally, it's potassium acetate and dinitrogen tetroxide. And so let's go ahead now then and get into our next topic. So now we're going to get into some of the ways that we count atoms and that we count molecules and methods that we have for working with what are incredibly large numbers typically of atoms and molecules. And so when we talked about atomic structure, I talked about just how incredibly tiny an atom is. To give a little bit more perspective for that. So the water in my glass right now, it's only filled about halfway. And I forget the exact number, so don't quote me, but there's somewhere around 1 × 10 to the 20th water molecules in here, if not more. It's 10 to the 20th, 10 to the 22nd, somewhere around there. But it's a 1 followed by 20 or 22 zeros water molecules. So that's a lot. And so we need a way to deal with numbers that are that large in a convenient way. And yes, we talked about things like the metric prefixes and scientific notation, but we need to even be able to talk about that in a simpler way than that. And so that's really what this lecture is all about. And so we're going to start off by talking about a concept called the mole. We'll look at how we do conversions with what we call the mole. And then we're going to investigate something that we call empirical formulas and how we can find those. And so to start things out, the mole. The mole is chemistry's essential counting unit. The definition of a mole from a chemical perspective is that 1 mole is the amount of a substance that contains as many particles as there are in 12 grams of carbon-12. And so that's our base scientific definition of the mole, is it's the number of atoms of carbon-12 that we have in 12 grams. We're not going to use sort of that definition much, but that is the technical definition of a mole. The way that we're really going to use it is that a mole is a counting unit, and that 1 mole of things is equal to 6.02 times 10 to the 23rd of that thing. And that's all it is. So some people kind of complicate this concept a little bit, but that's truly all that it boils down to. Is that if you have 1 mole of anything, you have 6.02 times 10 to the 23rd of that thing. And that's all that it really is. Now, it is important to note that this is just a really, really huge number. And so it has to be, though, because we use it to count really, really tiny things. We use it to count the number of atoms, count the number of molecules, and so forth. The number itself is called Avogadro's number, and here it is taken out to several more decimal places. 6.0221415 times 10 to the 23rd. We'll typically just round off to 6.02. That's plenty accurate enough for our purposes. But it is named after Amadeus Avogadro, an Italian scientist, lived in the late 17th and early 18th century. And so we just call this number Avogadro's number. And we say that there are Avogadro's number of particles in any mole, in a mole of any substance. So a mole of something contains Avogadro's number of that thing, contains 6.02 times 10 to the 23rd. Again, it's a huge number, and I can't stress that enough. It's a phenomenally big, can't even truly wrap your head around it number. And so picture 602,000 times a million, times a million, and times a million again. It's this. That's just ridiculously big. To put into perspective just a little bit, the Milky Way galaxy has in the neighborhood of 1 times 10 to the 10th stars. And so 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you had a 1 right here, that's the number of stars in the Milky Way. We then take this out to another 10 zeros and 602 to get us to Avogadro's number. And that's just 1 mole. So it's a phenomenally huge number. But again, it's just a counting number. When we say we have a mole of something, it's just a counting number. It is a chemist's version of saying a dozen. If you have a dozen of something, you have 12 of that thing. Same thing here. If I have a mole of something, I have this many. I have 6.02 times 10 to the 23rd of that thing. So just to reiterate that, I mean, if we're counting numbers of socks, we're going to probably count in terms of pair. There are 2 pairs per sock. If we're counting numbers of eggs, we're probably going to count in terms of a dozen, 12 eggs in a dozen. If we're counting pencils, okay, now we might count in terms of a gross. A gross is a dozen, 144 of that thing. Paper, we count in reams, 500 pieces of paper in 1 ream. Beer, we will quite often count in a case, and that's 24. Side note, my wife is Canadian, and they refer to cases as a 2-4. I'm going to go pick up a 2-4 of beer. But then if we're counting in terms of atoms or molecules or ions, anything down in that size range, we're going to count in terms of a mole, 6.02 times 10 to the 23rd. Now, remember when we talked about atomic weight earlier, a couple lectures ago, and we used units of atomic mass units, AMU. And I said that really AMU doesn't have much use for us now. It's just sort of a unit that we use. Atomic weight is going to start to mean something for us now. Atomic weight, or the molar mass, is also equal to the mass in grams of 1 mole of a substance. And so the molar mass is equal to the atomic mass of any element. And so again, it's a number you find in the periodic table, usually in the lower portion of each element box. Magnesium, we see that the atomic weight, 24.305. This means that there are 24.305 grams of magnesium in every mole of magnesium. If I have 6.02 times 10 to the 23rd atoms of magnesium, that's going to weigh 24.305 grams. If I have 6.02 times 10 to the 23rd atoms of carbon, that's going to weigh 12.011 grams. And so now molar mass is going to have this meaning for us. When we talk about molar mass, what we're really talking about is the number of grams. Sorry, that little, you'll see that thing pops up all the time during my lectures and it drives me nuts, but then there it is. It's the number of grams per 1 mole. And so 24.305 grams per 1 mole. And again, we see that everywhere in the periodic table. Phosphorus, 30.97 grams per 1 mole. And so this just gives you an idea of just the actual amount involved with some various elements. And so each of these are 1 mole of that element. So we see some copper here, sulfur, magnesium, tin, silicon, so forth. Along with finding the molar mass of elements, we can find the molar mass of entire compounds. All we do is we add up the molar masses of all the elements. That's it. So if we want the molar mass of sodium chloride, NaCl, and the units of all these are grams per mole, by the way. I just didn't write them out every time, but all of these units are grams per mole. So the molar mass of NaCl, we look up Na, it's 22.99. We look up Cl, 35.45. Add those up, and we get a molar mass of NaCl of 58.44. Something like glucose, C6H12O6. Now we have to take into account how many of each atom that we have. So we have 6 carbons times its molar mass of 12.011. Gives us a little over 72. 12 hydrogens times its molar mass of 1.08. Gives us 12.96. 6 oxygens times its molar mass of 15.99. And then we add those all up to get a total molar mass of glucose of 180.97. So that's all we have to do for molar mass. If you're finding the molar mass of something that contains a polyatomic ion, don't forget to distribute through the actual number. And so, for instance, iron 3 nitrate. The iron, there's only 1, 55.85. Now we have NO3 3. Now this is why, one of the reasons, again, why it's so important to recognize polyatomics and recognize that when I say NO3 3, what I'm really talking about is 3 of these, 3 of this NO3 complex. And so what I really have in this compound is this. Oh, I have no idea why I added an extra O in there. Sorry about that. Got carried away. That's better. So this is what I have, is I have 3 of these kicking around in there. And so I have 1, 2, 3 nitrogens. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygens. And so I take that into account in my molar mass. 3 nitrogens times 14.007, 9 oxygens times its molar mass of 15.999. I add those all up to get a final molar mass of iron 3 nitrate of 241.86. And this is just the molar mass of a few different compounds where we've done that same thing. The active ingredient in aspirin, acetyl salicylic acid, C9H8O4, and its molar mass, copper 2 chloride, dihydrate. We're not going to talk a lot about hydrates in this class, but there are some compounds, in which there are various numbers of water molecules attached to each of those. And we would take that into account. In this case, copper chloride. Every copper chloride molecule has 2 waters attached to it. And so this 170.5 takes those 2 waters into account. Iron 3 oxide. Here's some pure rust staring at you. Looks like they could have scraped that off my 1988 Subaru wagon. Great car. Love that car. Had that when I was about most of your ages. I was, I think, 21, 22 when I had that car. And then the molar mass of H2O, 18.02. But again, all these are found in the way that we just looked at, just by adding up the molar mass of all the different elements in the compound. Now, the two numbers that we've just talked about Avogadro's number and we've talked about molar mass. Hopefully, with as much as I've tried to talk about dimensional analysis, you're starting to think in terms of conversion factors, because both of those numbers, Avogadro's number and molar mass, are nothing more than different conversion factors that we're going to use in whichever way we need to use, depending on the problem that we're trying to solve. Avogadro's number, we could either think of that as 6.02 times 10 to the 23rd atoms per 1 mole, or we can think of that in the terms of 1 mole contains 6.02 times 10 to the 23rd atoms. And we would place that into our dimensional analysis boxes accordingly. If we knew the number of moles and we wanted atoms, then we're going to use our top version. If we know the number of atoms and we want to find the number of moles, then we're going to use this bottom version and put Avogadro's number down bottom in our denominator to get atoms to cancel out and be left with moles. Likewise, molar mass, same thing. When we're looking at the mass of iron 3 nitrate, we can either say that there are 241.86 grams of iron 3 nitrate per 1 mole of it, or that there's 1 mole of iron 3 nitrate per 241.86 grams of iron 3 nitrate. So again, either way, depending on what problem we're trying to solve, what information we have, and what information we're looking for. But these are nothing more than just different conversion factors that we're going to use to convert back and forth between either atoms or molecules, whatever it is that we're actually looking for, but atoms or molecules and moles, or back and forth in between grams and moles. As a side note, if I were you, as you get into doing some of these problems and doing some of this practice, you'll note here that I didn't just simply write 241.86 grams per 1 mole. I wrote out the actual elements or the actual compounds involved. I would take the time to do that if I were you. The reason for that will become more apparent in a few weeks when we get into writing out some fairly long equations, when we start looking at the amounts of things in chemical reactions in a unit called stoichiometry. But if you get into that habit now of always being this particular, writing out not just grams per mole, but grams of iron 3 nitrate per mole of iron 3 nitrate, get into that habit now and you'll be doing yourself a big favor in a few weeks, when it's going to help you keep things organized by writing that out. So that's just a side note. I mean, you obviously don't have to. Whatever method works for you is fine. But that's my opinion as somebody who has been doing this a long time and watching a lot of students do this for a long time, is that you will absolutely be doing yourself a favor if you are this particular when you're writing things out. So take that advice for what it's worth. If you're more of, and I also say, in saying that, I realize that dimensional analysis, even though I think it is the best problem solving method of all time, pretty much, for some people, it just doesn't click. And so other people are more of just sort of let me memorize, multiply or divide, depending on what I'm trying to do. If you're that sort of person, then this sort of flow chart is something that I developed to help you out. And so you'll notice that sort of central in this whole thing is moles. And you'll find that as we go on in this course, that with many of the different types of calculations that we do, moles are sort of central to the whole thing. That a lot of calculations we do are going to flow through moles in one way or another. We're going to have some sort of given information and convert to moles, use that to convert to something else, and then use moles to convert to a final thing. But a lot of calculations will flow through that general pathway. And so this is a flowchart that you can use, that you can find. Let's say you know the number of grams of something you have and you want to calculate the number of moles. And okay, this tells you you're going this direction. You see our arrow down here going from grams to moles. So we're going to use the molar mass and we're going to divide. So we're going to take our grams and divide by our molar mass to get to moles. If we know our number of atoms or molecules, we're going to divide by Avogadro's number to get to moles. If we know the number of moles and we're trying to get to grams, then we're going to multiply by the molar mass to get to grams. and so forth. The moles, the atoms, or molecules will multiply by Avogadro's number. You will you will have calculations, or you have to get maybe from the number of grams to the number of atoms. So again, you could either set up some dimensional analysis, and I'll show you that in just a second, or you could say that, okay, I'm going to take grams and divide by my molar mass to get to moles, and then multiply by Avogadro's number to get to the number of atoms or molecules. Don't worry too much about this molarity down here for now. This is something that we will be using in a few weeks. I built it into this flowchart because molarity is something that is very much going to be involved in some different calculations that we do later on. And so it's handy to just include it in this overall flowchart that I made. Again, we're not going to really use it for much just yet, but be aware that that is something that will be coming down the pike. And so this is just an example. And so here we're going from the number of grams of carbon. We have 16.5 grams. And in order to go from mass to moles, so you can see here our dimensional analysis setup, and we've actually set it up down here. In order to go from mass to moles, we're going to put our conversion factor, our molar mass, in like this: 1 mole of carbon per 12.01 grams of carbon. We can see that our grams of carbon cancels out to leave us with moles of carbon, which is what we're looking for. And so then we would take 16.5 divided by 12.01, gets us to 1.37 moles of carbon. We do have to be mindful of significant digits. Note that there are 4 significant figures used in the molar mass, but our original measurement here only had 3. So our final answer has 3 significant figures. Typically, you'll find that molar mass won't be a factor in looking at your number of significant figures, just because molar mass is usually going to be taken out to more significant figures than what your measurements are. And what I would do with molar mass if I were you is always keep the same number of significant figures as what you have in whatever periodic table you're using. Don't round it off. If you're using, for instance, we just pull up the periodic tables that I have that I recommended you to use. So if you're using this periodic table here, then don't ever round these off. If you're, take iron, 55.845, and use all of that, and then keep those significant figures in your measurements. It's just going to make your calculations come out that much more accurately. And so here's an example then. We want to know how many magnesium atoms there are in 150.0 grams of magnesium. And so the basic solution, and we've looked at this, our basic pathway is that we're going to use the molar mass of magnesium from the periodic table and Avogadro's number. The question is how we're going to do that. How are we going to set things up? And so I'd recommend that you go ahead and pause the video now, try to do this calculation, and then we'll come back and look at the whole flow. We'll look at the solution. And so pause the video now and give this a whirl. Okay, so let's now look at the answer. So we're starting with 150 grams of magnesium, 150.0. So we're going to use our molar mass, 1 mole of magnesium per 24.305 grams. And so that's going to cancel out grams for us. And then we're going to use Avogadro's number, 6.02 times 10 to the 23rd magnesium atoms per every mole of magnesium. And so when we do this calculation out, 150, everything up top, 150.0 times 1 times 6.022 times 10 to the 23rd, divided by everything down bottom, so divided by 24.305. And we come up with a final answer of 3.717 times 10 to the 24th magnesium atoms. Again, 4 significant figures, because our initial measurement had 4 significant figures. So we have 4 significant figures here, and this is also a huge number, which is what we would expect. We're calculating the number of atoms. So we know that's going to be a huge number because atoms are so small. Always take those few seconds and think about if your answer makes sense. If you're coming up with an answer to a question like this, and you calculate things through and you come up with something like 72 atoms, you can guess that there's probably something wrong there. You've probably done something incorrect because 72 atoms is nothing. And so 72 atoms wouldn't even measure on all but the most expensive instruments. And so if you're not getting things that are this big when you're counting the number of atoms, you probably made a mistake somewhere. So take that time to just think about something. It might even be something as simple as you forgot to include this part that your calculator gave you. And so you just wrote down 3.717. Then you go back and say, oh, this part was there too. So just, again, take that time to think about your answers and if they make sense or not. Same thing, so give this one a whirl. How many grams of chromium there are in chromium-3 acetate? So see what you might be able to come up with here. So the first thing that we want to do is come up with our formula for chromium-3 acetate so that we can find the molar mass. Then we're going to use our 25.1 grams, and then use our molar mass. We'll divide by our molar mass to get to moles, but we're not quite done. We're looking for grams of just chromium here, not chromium acetate. Our question is asking us for grams of chromium. So we do want to recognize that there's one mole of chromium per 1 mole of chromium acetate. Now, yes, I realize mathematically this step is 1/1, and so mathematically it doesn't need to be there. But for our units to work out, it absolutely does. And so you would want to include that in your work, just to show that you are going from moles of chromium acetate to now moles of chromium, because this won't always be 1/1. For instance, if we were looking for the moles of carbon, we can see that there are, so in every 1 acetate, there are 2 carbons. There are 3 acetates. So for every 1 chromium acetate, we would have 6 carbons. And so we would reflect that in here. So again, though, this one is just chromium, so it is 1/1. But then we're going to use the molar mass of chromium, 52.00, and then finally come up with our final answer of 5.70 grams of chromium. So if you got completely lost here, that's okay. But go back, take the time to go back and look through this and make sure that this makes sense. Because this type of calculation and this type of pathway that we took in this calculation are going to be something that we're going to do very commonly in this course. And so make sure that you're comfortable with this and that this makes sense to you. And now I've got a whole bunch more practice problems for you. And so go ahead, pause the video now, and just run through these. See what you can come up with, the answers to all these problems. So pause the video now, see what you can do. And now just check your answers. And so again, maybe pause the video here, and just so the answers are up on the screen for you, check through everything. Any that you got incorrect, go back and see what you might have done. Go back and check your answers and see where you might have gone wrong. So another practice example here. So the average daily requirement of the amino acid leucine, C6H13O2N is its chemical formula. So the average daily requirement of this amino acid is 2.2 grams for an adult. So what I want you to do is several things. I want you to calculate that in moles, so how many moles of leucine are required daily. And then figure out how many molecules that really works out to. So how many molecules are recommended that we ingest into our body on a daily basis. And then figure out how many nitrogen atoms that is, and then how many carbon atoms. So again, as we quite often do, pause the video here and see what you can work up with for these answers. Hopefully these are what you got. Okay, so now we're going to move on to something we call percent composition. Percent composition is something that we can use is an analysis method, or there are analyses methods that lead to percent composition that help us to characterize something that might be an unknown, some sort of unknown compound that we don't know what it is, we're trying to figure it out. There are different methods or there are different analytical tools that we can use to figure out the percent composition of these unknown compounds, which can then be used to calculate what we call an empirical formula. And we'll talk about what that is in a little bit. But percent composition essentially is, if we have a compound, we just want to know of the different elements in there, what percent of that compound by mass is that element. And so something like glucose, C6H12O6, what percentage of that is carbon? What percentage of it is hydrogen? What percentage of it is oxygen? Now remember, we're looking at percentage by mass, not the percentage of all the different types of atoms in there. We're looking at a percent by mass. And so in other words, if I had, for instance, 100 grams of glucose, how many grams of carbon is that? How many grams of hydrogen is that? How many grams of oxygen is that? That's what percent composition is. To calculate percent composition, we're going to take the number of atoms of that element within the chemical formula, multiply that by the atomic weight, and divide it by the formula weight of the compound. And so if we look at an example here, so we want to know the percent composition. We'll eventually find all of the elements, but we're going to find the percent composition of calcium in calcium hydroxide. So we've got our generic formula up here. And so in calcium hydroxide, there's one calcium atom. We're going to multiply that by the atomic weight of calcium, which is 40 grams per mole. Divide that by the atomic weight of the whole thing, divided by the atomic weight of calcium hydroxide here, which is 74.41. And then we multiply by 100 to convert to a percent, which gets us to 54%. And so a random sample of calcium hydroxide will be 54% calcium by mass. And then we do the same thing for the other elements. We're going to find that for oxygen. So in CaOH2, there are 2 oxygen atoms. So times the formula weight of oxygen, which in this instance we just rounded to 16.0, divided by the formula weight of the whole thing, gives us 43.2% oxygen. And then finally for hydrogen, we run through the same exact process and we get 2.72% hydrogen. Now, what should all of those add up to? If we take the percent composition of each of those 3 elements, they should add up to 100. And we find that they pretty much do. I mean, they add up to 99.92%. And so, yes, that's off by a little bit, but we can attribute that to some various rounding. Oxygen, for instance, is 15.999 for an atomic mass. We rounded it to 16.0. And just some rounding differences in the way that we did the calculation. So if you're getting something like 99.92, then you're okay. If you do your check at the end and you get something like 72 or 146, then you made a mistake somewhere, go back and check it. And so another way to sort of go about this is that it's the same exact method, but a way that I might set these up as well is, so if we're trying to find the same thing, we want to find the percent composition of each element in CaOH2. If I know that I have to find the percent composition, I'm just going to very carefully keep track of everything as I calculate my atomic mass. So I'm going to go Ca, I know there's 1 of those at 40.0. Oxygen, I have 2 times, actually I'll stick with what we used here. We used 16.0, so 32. Hydrogen, 2 times 1.008, so 2.016. And then I add those up, and I get whatever that added up to. What was it, 74 point something, 40 plus the, should probably be able to do that in my head, but so we get 74.016. And so then if I want to find the atomic mass, I'm just going to take each of these that I already have. In case of calcium, 40 divided by 74. Oxygen, 32 divided by 74. Hydrogen, 2.016 divided by 74. And so it's the same exact thing. I just happen to have already done some of the work in calculating my atomic mass. And so, not sure why I wrote, calcium, 40.0 divided by 74.016. And times 100 to convert to a percent. Oxygen. And if I do all those out, I'll come up with the same percentages that I had here. So again, same exact process. It's just if you're already calculating the atomic mass, you're essentially already doing some of the work involved in the examples that we looked at just a second ago. It's just a different way of looking at it. And so that leads us to talking about something called empirical formula. An empirical formula only shows the simplest ratio of atoms in a chemical formula. Ionic compounds, for instance, are always represented actually by their empirical formulas. A molecular formula shows the actual composition of the molecule, shows not just the simplest ratio, but how many of each atom exist in each molecule of that compound. And so let's just revisit real quick sort of one of the differences between ionic versus covalent compounds. Remember, we talked very briefly about the fact that ionic substances exist in these lattice type structures. So if you were to look at something like NaCl at its molecular level, you're going to see this lattice of alternating Na and Cl ions in there. And that's how it really exists. You don't have what we would call a discrete molecule of ionic compounds. You don't have little like an Na and a Cl. So here's an NaCl molecule floating around in space. That's not what exists for ionic compounds. What exists is this crystal and this lattice structure. And so we represent an ionic formula then by its empirical formula. It's always just the simplest whole number ratio of the ratio of ions within that lattice. That's different from molecular or covalent compounds because those actually do exist as discrete molecules. And so in the case of glucose, C6H12O6, here's what a glucose molecule really would look like. Here's our 1, 2, 3, 4, 5, 6 carbon atoms. H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6 O's. And so at the molecular level, this is really what a molecule of glucose will look like. They do exist as individual molecules floating around. And so we write out the chemical formula showing how many of each of those atoms actually do exist in each of those little discrete molecules. And so we can, though, if we want to, and we'll see why a little bit here, but also later on in the course, it's useful for us to also know what the empirical formula is of a molecular compound. So remember that an empirical formula does just give us the simplest whole number ratio. And so if we look at glucose as an example, remember the molecular formula we said was C6H12O6. So that's what actually exists. That is a glucose molecule. It has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in there. It is useful, though, for different analyses that we do, for us to also know the empirical formula of glucose, to know just the simplest whole number ratio of all of the elements in there. And so we just simplify that down. And so we get, in the case of glucose, we simplify this down and we get CH2O. And so that is our empirical formula. And so we should note that it is entirely possible for different compounds to have the same empirical formula. And so if I have CH2O as an example, and so CH2O is my empirical formula, then I might very well have a molecule that's maybe C2H4O2. That could be some type of molecule. We looked at glucose, C6H12O6. I might have something that is C24. H48O24, something really big and huge with all of this stuff thrown in there. And so that's something else, could be something else for a molecule. But they would all, so these are the molecular formulas of each of those, they would all reduce down to the same empirical formula. And so that is just something that's important to note, is that different molecules can absolutely have the same empirical formula. And so for each of these formulas below, I want you to consider if it is an empirical formula, if it is a molecular formula, Or if, given what you possibly know of the compound, is it possibly both? Is it maybe both an empirical and a molecular formula? So we have H2O and H2O2, as well as HO and C6H12O6. So what do you think about those? Okay, so H2O. H2O is an empirical formula, that's for sure. We also know that it is the molecular formula of water. And so H2O is both an empirical and a molecular formula. H2O2, hydrogen peroxide. In this case, just a molecular formula, right? Because that's not the simplest whole number ratio. HO. Now, you might not have all the tools to necessarily know this, but I would say that H2, when we're looking at a compound, H2 would be just an empirical formula. It is the empirical formula of H2O2. Now, yes, there is the polyatomic ion, hydroxide, OH-, but that's a little bit different. And then finally, C6H12O6, for reasons that we just looked at, absolutely just a molecular formula, not an empirical formula because it's not reduced all the way down. And so we can find an empirical formula by using the percent composition of a compound. And so if we look at our steps in order to do so, the first thing that we would do is we would convert our mass percent to just mass. So the way that we do that, and we're going to look at several examples, but the way that we do that is by assuming that we have 100 grams of whatever molecule it is we're looking at. And so if I know that something is 54.2% by mass, then I'm going to say, okay, I have 54.2 grams of that. After that, I'm going to use the molar mass to convert that number of mass, convert the mass of that element, over to moles of that element. And I'm going to do that for each atom or each element within the compound. I'm then going to divide all of them by the smallest number of moles. And I know this is a little bit confusing, just think of it this way. We're going to look at some examples. And then for our final step is to convert to a whole number ratio. So let's look at this. So here we have an example of a compound that we find to be 64.82% carbon, it's 21.59% oxygen, and 13.59% hydrogen. And we want to find the empirical formula. And so the first thing that we're going to do, like I said, is assume that we have 100 grams of the compound. And so we're going to say that we have 64.82 grams of carbon, 21.59 grams of oxygen, and 13.59 grams of hydrogen. Our second step is to now take each of these number of grams and use the molar mass of each of these elements to convert that over to the number of moles. And so just use the molar mass like we have before. And we find this number of moles of each of those different elements. And so step 3, what we're going to do now is to divide each of these by the smallest one. As we see that the smallest one is our oxygen here, our 1.349. So we're going to divide each of them by 1. And that's going to give us our final subscripts. And so the 5.397 moles of carbon, we're going to divide that by 1. That will give us or divide that by 1.349. That will give us our subscript for carbon. For oxygen, 1.349 divided by 1.349 will give us our subscript for oxygen. Hydrogen, 13.48 divided by 1.349 will give us our subscript for hydrogen. And so we can see that here. So there's our carbon, 5.397 divided by 1.349 gives us 4.001, basically 4. We do that for hydrogen. We get 9.992, pretty much 10. And obviously for oxygen, 1.349 divided by itself equals 1. And so those are our subscripts for our empirical formula. C4, H10O. Sorry, yeah, that other slide was one that, sorry, shouldn't have slipped that one in there. But there we go, C4H10O. Now, sometimes, or sorry, for compounds in which the empirical formula is not also the molecular formula, you would then have to scale up to find the actual molecular formula. And you would do that if you also knew the molar mass of the compound. And so let's look actually back at this example here. And so C4H10O. So this is our empirical formula. And so let's say that I also told you that we knew the molar mass. And so this is maybe some unknown compounds. Again, we've run some analysis on this, and we've been able to find that the empirical formula has this, or that this is the empirical formula. This is something that's still unknown. We don't know what this actually is. We're able to do some other analysis on it, though, and we are able to find that the molar mass of our unknown equals 148.2 grams per mole. We can use that to find the actual molecular formula of our compound. What we're going to do is we're going to find the molar mass from our empirical formula. And so carbon, our 4 times 12.01, our hydrogen, we have 10 times 1.008. Our oxygen, we have 1 times 15.999. We add those all up and we get 74.1 grams per mole. So, oh, sorry. I'll sometimes forget to do that and you're not able to yell at me because you're watching a recording, but here we are. And so that was just me. I was just writing all that out before. And so what we have now is our empirical formula, molar mass. So C4H10O would weigh 74.1, but yet we know that the molar mass of our actual unknown is 148.2. And so hopefully you see where this is going. Wrong button, here we go, there we go. 148.2 divided by 74.1 gives us a number 2. That tells us how much to scale up our empirical formula by. We take C4H10O and multiply everything by 2. C8, H20, O2, and that would be the actual molar mass of our compound. And so that's why empirical formula and percent composition are important, because what we can do is we can actually run an analysis, and we're going to look at it deeper at that analysis in a few weeks from now. But we can run an analysis to get us this information here, to tell us the percent composition of a compound. We can also run an analysis that will tell us the molar mass of a compound. So if we have some unknown hydrocarbon, if we have some substance that contains only carbon, hydrogen, and oxygen, we can run it through these analyses and find the actual molecular formula of that compound. That's powerful stuff. And so we can use again, some analyses that we'll talk about later to find our percent composition, which can get us to our empirical formula. We can then use a mass spectrometer to find the actual molar mass of the compound. So we could use then those two bits of information together to get to the actual molecular formula of a completely unknown compound. That's powerful stuff. That is a powerful type of analysis to be able to do. That's one of the reasons why this stuff is important. And we actually just went through all of this. Oh, and actually I forgot that I had an example here, a different one, so same idea. And so in another case, we found the molar mass of a completely different molecule to be 222.1. So same thing, 222.1 divided by 74.12 would give us 3. We would scale everything up by a factor of 3 to get to a formula of C12H30O3, another completely different molecule. And so let's do a few practice runs. And so methanol, 37.48% carbon, 12.58% hydrogen, and 49.93% oxygen. I want you to find the empirical formula. So again, these are the steps that you're going to do. You're going to convert to mass, convert to moles, then simplify your molar ratio, and then write out the empirical formula. Note as you do so that hydrocarbons are typically written in the form of the carbon, hydrogen, and oxygen in that order with their appropriate subscripts. So go ahead and pause the video and see if you can come up with the empirical formula of methanol. And let's walk through it now. And so, good, there's all my necessary information. And so 37.48% carbon, 12.58% hydrogen, and 49.93% oxygen. So again, my first step is just convert all of those to grams. And so I'm going to have 37.48 grams of carbon, 12.58 grams of hydrogen, and 49.93 grams of oxygen. I'm then going to just convert each of these to moles. And so 1 mole of carbon, 12.01 grams of carbon, 1 mole of hydrogen, 1.008 grams of hydrogen. Sorry, that one was so messy. 1 mole of oxygen, 15.999 grams of oxygen. And I haven't actually done these out yet. Probably should have, but I didn't. 37.48 divided by 12.01. 3.12. 12.58 divided by 1.008. 12.48, and then 49.93 divided by 15.999, 3.12. So now I just divide each of these by the smallest one. In this case, the smallest one is the same for both, both carbon and oxygen have our smallest number. So I'm just going to divide everything by 3.12. So for carbon, 3.12 divided by 3.12 equals 1. For hydrogen, 12.48 divided by 3.12 is 4. For oxygen, 3.12 divided by 3.12 equals 1. And so my final empirical formula then is going to be CH4O. And there's my empirical formula for methanol. Here's another example. Magnetite, composed of only iron and oxygen, and it contains 72.36% iron by mass. And we want to know the empirical formula. Sorry. So it's the same exact strategy. So go ahead and pause the video now and see if you can find the empirical formula of magnetite. Now let's go through it. And so you might have thought at first that there was some missing information, but there really isn't. And so let's talk about that. And so we're told that the only elements present are iron and oxygen. And so 72.36% iron. So if the only things present are iron and oxygen, the remainder obviously has to be oxygen. So 72.3 or 100 minus 72.36 means that I have 27.64% oxygen. And so now I convert each of these over to grams, 72.36 grams of iron, 27.64 grams of oxygen, convert to moles. 1 mole of Fe, 50, directly behind me, of course, 55.845. oxygen, so now I calculate them out, 72.36 divided by 55.845, 1.29. And for oxygen, 27.64 divided by 15.999, gives me 1.72. So iron, 1.29 divided by 1.29 equals 1. For oxygen, 1.72. Sorry, wow. There we go, 1.72 divided by 1.29. 1.3 repeating. So now we do have a bit of an issue. So let's just go ahead and write this out. So I do have 1 iron and 1.3 repeating for oxygen. Now I obviously can't have that. Now, in the case of like we saw earlier, I mean, if you get something like, 1.92, then you could round that to 2, or 4.07. Okay, we're going to round that down to 4. But we can't round something like 1.33. What we can do is scale that up, though, so that we do get to some whole number ratios. And that's what we have to do here. If we multiply 1.33 by 3, that gets us to 4. And so we would do that to each of these. And so we're going to scale this up then to Fe3O4 would be our empirical formula of magnetite. And then just one last example. Hexamethylene diamine. It's one of the materials that's used to produce one of the a type of nylon. And so we run this through an analysis, and we get 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. So we want to know again, what's the empirical formula? We also know that the molecular weight of this compound is 116 grams per mole, and so we want to use that to find the molecular formula. So just like before, go ahead and pause the video and see what you can come up with. And hopefully you're back. And so let's run through this analysis. And so we have 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. So again, we just convert all those to grams, 62.1 grams, 13 grams of carbon, 13.8 grams of hydrogen, 24.1 grams of nitrogen. Convert all of these to moles. You'll see that quite often when I do calculations like this, I like to set up all my calculations before I actually get my calculator out. Just a little bit more time efficient, but there's no reason that you couldn't just run these calculations as you worked it out. Either way, it obviously is the exact same. So then I plug all of these in. I get 62.1 divided by 12.01 for 5.17. 13.8 divided by 1.008. 13.69 and 24.1 divided by 14.007. 1.72. So I'm just going to divide each of these by the lowest one, being the 1.72. And so for carbon, 5.17 divided by 1.72. 3.00. Hydrogen, 13, go away. 13.69 divided by 1.72. 7.96, and nitrogen 1.72 divided by 1.72 equals 1. And so that then gives us, sorry about that, that gives us our subscripts in our empirical formula of C3H8N. So there's our empirical formula. I always spell that wrong, don't I? Yeah. I've spelled that word wrong for 20 years. So there's our empirical formula of hexamethylene diamine. I could spell hexamethylene diamine, but I can't spell empirical. Anyway, there's our empirical formula. We want to actually know the molecular formula, though. And so what we're going to do is find what the molar mass is from our empirical formula. So we're going to take our carbon, our hydrogen, and our nitrogen, and we find (58.2 grams per mole). And so then we're going to take our molar mass, the 116 that we were given, divided by the 58.2. That basically gives us 1.99. And so that tells us then, I'm kind of running out of space here, but that tells us that we need to scale up our empirical. So here was our empirical formula here. We're going to scale up our empirical formula by a factor of 2 in order to get to our molecular formula. And so we're going to have C6H16 N2, and that then is our final molecular formula for hexamethylene diamine. And there we go. So once again, like we've seen in so many of these lectures so far, and we'll continue to see, that's a lot of information. And I know that that is a whole bunch of stuff to digest, but that is it for today. And so this brings us then to within just one more lecture for all of our Unit 1 material. Sorry, 2 more lectures for our Unit 1 material. So we're most of the way through. In the next lecture, we will start talking about chemical reactions a little bit, starting to take some compounds, mix them all together, throw them together, and see what happens. And then we'll spend a couple lectures on that, and then getting ready for our first test. And so, as always, if you do have any questions, definitely be sure to shoot me an email. But like most things in chemistry, like I said, I know there's a lot of information, a lot of stuff that we've gone through here. The best way to master this, the best way to get good at it, is to do problems. Do tons of problems. If you go to our website, Unit 1 materials, you'll find, once again, remember, you'll find some supplemental videos. This is a video here just on moles and molar mass that we talked about. I don't think I have one on empirical formulas in there, but I do have a bunch of extra practice. So if you're looking at some more practice in doing mole calculations, and sure enough, here we go. Here's 4 pages worth of finding the molar mass, finding the number of moles, finding the number of grams, finding the number of atoms. And so there's a ton of practice out there available for you. Use it. That's how you're going to learn. That's how you're going to get good at this stuff. Do this sort of practice before you move on to Chem 101. This will get you the foundation. This practice will get you your foundation before you go on and do stuff that's going to be counted for a grade. So that's just a little bit of advice on one of the ways to be successful in this class. One of the other ways is be sure to communicate with me. Send me an email if you have any questions. Until then, have a good day.